March 15, 1944, 27,000 feet above Brunswick, Germany. Captain Robert Johnson squints through the frosted windscreen of his P-51 Mustang, scanning the crystalline sky for the glint of sunlight on metal that means enemy fighters. 6 miles below, a stream of B-17 Flying Fortresses drones eastward toward Berlin. 200 heavy bombers carrying destruction into the heart of the Third Reich. And for the first time in this war, American fighters are going with them all the way. The temperature outside is 45 degrees below zero. Johnson's breath fogs inside his oxygen mask as he checks his fuel gauges for the third time in 10 minutes. They launched from Debden, England, 3 hours ago. They've already flown farther than any American fighter escort mission in history, 430 miles from base, deeper into Germany than Spitfires or Thunderbolts could ever reach. And incredibly impossibly, his Mustang still has fuel for another 2 hours of flight. Horseback leader, this is Nuthouse. Bandits, 12 o'clock high, Angels 30. Estimate 20 plus. The radio call snaps Johnson's attention forward. They're 7,000 feet above and slightly ahead, dark specks materializing against the pale sky. Bf-109s dropping from the sun, positioning for a diving attack on the bomber stream. Horseback flight, punch tanks and climb. Let's take them head on. Johnson's thumb hits the drop tank release. 2 108-gallon fuel tanks tumble away from his wings, falling toward the German countryside far below. The Mustang, 72,000 pounds lighter, leaps forward as Johnson advances the throttle. The Packard-built Merlin engine responds with a throaty roar, its 2-stage supercharger forcing pressurized air into the cylinders, maintaining sea-level power at this oxygen-thin altitude where lesser engines gasp and falter. The P-51 accelerates in a steep climb, its laminar flow wings slicing through the thin air with minimal drag. Johnson's airspeed indicator shows 380 miles per hour and climbing faster than the German fighters above. Faster than any escort fighter has a right to be at this altitude, this far from home. Tally-ho! Engaging. The two formations merge in a ballet of violence. Johnson's Mustang flashes past a Messerschmitt, so close he can see the pilot's face, young, blonde, eyes wide with surprise at finding American fighters here, over Brunswick, where no American fighter should be able to reach. Johnson pulls into a hard left turn, the G-forces crushing him into his seat, his vision tunneling as blood drains from his brain. The Mustang's turn radius is tighter than the 109's, another advantage of Schmued's obsession with aerodynamic efficiency. Johnson completes a 360-degree turn in less space than his opponent, slides onto the Messerschmitt's tail, and fires a 2-second burst from his 650 caliber machine guns. Tracers streak across the gap. Pieces of the 109's tail section tear away. The German fighter rolls inverted and dives, trailing smoke. Johnson doesn't follow, can't follow. His job isn't hunting kills, it's keeping the Luftwaffe away from those bombers. He levels out, scanning for more threats, and sees the German formation breaking apart. The 109's scatter, unwilling to engage in sustained combat this far from their bases, this deep into what should be Luftwaffe-controlled airspace. They're retreating. The Germans are retreating over their own territory. 3 months ago, such a thing would have been unthinkable. American bombers struck German targets defended only by their own guns, suffering horrific losses. 60 bombers lost in a single raid over Schweinfurt, 600 men killed or captured in one afternoon. The 8th Bomber Command was being bled white because its fighters couldn't escort past the German border. Now Johnson and his squadron are 430 miles from England, turning back a Luftwaffe attack over Brunswick, and they still have enough fuel to chase the Germans all the way to Berlin if ordered. The impossible has become routine. Horseback flight, reform on me. Let's get these bombers home. Johnson settles into a steady orbit above the B-17 formation, watching the fortresses continue their bomb run while his Mustang sips fuel at an economical cruise setting. In the cockpit around him, every detail reflects Edgar Schmued's obsessive engineering. The smooth, flush-riveted skin that reduces drag. The laminar flow wing profile that allows high speed with minimal power. The ventral radiator scoop that doesn't just cool the engine, but actually generates forward thrust through the Meredith effect. The internal fuel capacity that, even without drop tanks, exceeds any contemporary fighter by hundreds of gallons. This aircraft shouldn't exist. In 1940, when Schmued proposed building it in 120 days, experienced aviation engineers called it impossible. When he insisted on prioritizing aerodynamic efficiency over engine power, they called it backwards thinking. When the prototype first flew with its Allison engine and proved mediocre at high altitude, they called it a failure. Then someone had the idea to mate Schmued's brilliant airframe with Britain's Merlin engine. And everything changed. Johnson watches the German fighter's mere specks now disappear toward the eastern horizon. Behind him, the bombers press on toward Berlin. Around him, 16 P-51 Mustangs maintain their escort positions, each one burning fuel so efficiently that they'll land back in England with reserves to spare. 3.5 years ago, this aircraft existed only in Edgar Schmued's imagination, a set of radical ideas about wing design, engine cooling, and structural efficiency that conventional wisdom said couldn't work. Now it's winning the air war over Europe. The story of how that happened, how one engineer, this impossible ideas transformed aerial combat and helped win. World War II begins not in the skies over Germany, but in a modest drafting room in Inglewood, California, where a team of designers had just been given an impossible deadline. April 10, 1940. North American Aviation Headquarters, Inglewood, California. The request is extraordinary, bordering on absurd. Not produce someone else's aircraft under license. Create something completely new in 4 months. The RAF is getting mauled over Dunkirk. We have the tooling, the production capacity, the experience. It's the sensible option. The airframe is a generation behind what the Germans are flying. Atwood walks to the drafting table where preliminary sketches are spread out, existing fighter designs from across the industry, performance specifications, engine data. It's impossible. A conventional development program takes 18 to 24 months. Testing alone requires Edgar Schmued, the quietly brilliant Austrian-born engineer who serves as North American's chief designer. Edgar always thinks he can do the impossible, Atwood says, but there's respect in his voice. What's his approach? Yes, but Edgar thinks the P-40's problems aren't just the engine. The airframe is draggy, heavy, inefficient. 800, maybe 1,000 miles with drop tanks. Aerodynamic efficiency. A laminar flow wing that generates lift with minimal drag. And most radical of all, Kindleberger pauses for effect. He wants to design the lightest possible airframe. Strip out every unnecessary ounce. The Army won't accept a lightweight fighter. They want armor, redundant systems, durability. Atwood studies the calendar on the wall. April 10th to August 10th. 120 days. It's insane. But then again, the entire world situation is insane. Poland conquered in weeks. Denmark and Norway fallen. France about to collapse. Britain standing alone against Nazi Germany. Conventional wisdom has failed at every turn. Maybe it's time for unconventional engineering. If we commit to this and fail, we lose the P-40 contract. We lose British orders entirely. The company could go under. We produce an obsolete aircraft that won't save Britain and won't help us when America inevitably enters this war. But if Edgar succeeds, Kindleberger lets the possibility hang unspoken. Edgar Schmued stands at his table, already deep in calculations. Edgar, Kindleberger says simply, the key is understanding that horsepower alone doesn't determine performance. Schmued begins, his slight Austrian accent coloring the technical English. The P-40 has a 1,150 horsepower Allison engine. So will our aircraft. But the P-40 wastes perhaps 300 of those horsepower overcoming aerodynamic drag. The NACA has published research on airfoil shapes that maintain smooth, laminar airflow over more of the wing surface. This dramatically reduces drag compared to conventional wings where the airflow becomes turbulent. No one has successfully built a laminar flow wing fighter because the manufacturing tolerances are extremely tight. Any surface imperfection disrupts the laminar flow. The wing will be the most precisely manufactured component. A laminar flow wing gives us 50 miles per hour more speed than a conventional wing with the same engine power. Schmued moves to another sketch, a side view of the complete aircraft. Engine cooling is critical. The Spitfire has it under the wing better, but still draggy. If you design the duct correctly, the air heated by the radiator expands and accelerates as it exits. In theory, a perfectly designed Meredith effect radiator adds zero neck drag. In practice, we should achieve near zero. The idea of a radiator that produces thrust rather than drag seems to violate basic physics, but the mathematics support it. Compared to the P-40 at 5,800 pounds, we're heavier. Yes, but we're also larger and carrying more fuel. Compared to a Spitfire at 5,100 pounds. We achieve this through structural efficiency. Semi-monocoque construction, aluminum alloy throughout, nothing overbuilt. We're designing to exactly the required load factors. Plus 12 Gs, minus 6 Gs. Standard fighter maneuver envelope. Everything about this is risky, Schmued replies bluntly, but we have 120 days. We cannot afford the luxury of conservative design. Kindleberger studies the sketches, the calculations, the radical departures from conventional practice. This aircraft will have a wing unlike any production fighter, a cooling system that theoretically produces thrust, a structure engineered to the minimum acceptable weight, with two 75-gallon drop tanks under the wings, 330 gallons total. The escort missions everyone dreams about, bombers protected all the way to their targets and back, have been impossible because fighters run out of fuel. 4.50 caliber machine guns, one in each wing. The British 1.30 caliber guns, we're ignoring that. American armament standards are superior. If we're designing this aircraft, we design it properly. We'll propose the NA-73, completely new fighter design, delivered to prototype stage in 120 days. Edgar, you have carte blanche. Everyone else, he looks around at the assembled engineers, you're about to attempt something no one thinks is possible. Prove them wrong. Around him, slide rules click, erasers smudge, pencils scratch across paper. May 1940, North American Aviation Engineering Department. At 2:30 in the morning, Edgar Schmued stands at his drafting table under harsh fluorescent lights, refining the wing root fillet for the 7th time. The air is thick with smoke and the smell of blueprint developer fluid. Edgar, we have a problem with the laminar flow wing. Caltech's preliminary tests show the laminar flow breaks down at 14% chord, much earlier than predicted. Now Schmued looks up, his eyes red from fatigue but still sharp. Show me. The smoke flow visualization clearly shows the laminar airflow becoming turbulent too early in the wing chord. It asks exactly the problem that has plagued every previous attempt at laminar flow wings, theoretical perfection that disappears when reality intrudes. We use the smoothest possible model. Schmued studies the photographs for 30 seconds. Here, maximum thickness moved after 45% chord. Gentler pressure recovery. Test this. This affects everything: structural loads, fuel tank volume, aileron effectiveness. We'll need to recalculate. Rice nods and heads for the wind tunnel model shop. The wing problem illustrates their central challenge. They re-attempting to perfect in 4 months what typically takes years of iterative testing. Every component must work correctly the first time, because there's no time for major revisions. The Meredith effect, the theoretical thrust generated by heated air exiting the cooling duct, should work according to the mathematics. But getting the duct geometry precisely right requires computational work that's pushing their abilities to the limit. The exit area needs to be 1.35 times the inlet area for optimal thrust recovery. Horky announces to anyone listening, but if we make it too large, we get flow separation. Larry Waite, working on structural design, calls across the room, "Eddie, we need that radiator moved forward 3 inches. Horky looks incredulous. This is how the design evolves: constant compromises, everything affecting everything else. Schmued moves between the design stations, coordinating, deciding, solving problems. When disputes arise about conflicting requirements, his decision is final. If it adds weight without adding capability, eliminate it. If it creates drag, redesign it. The wing will use the NACA 45 to 100 laminar flow airfoil, modified per Schmued's adjustments, with a span of 37 feet, 4 50 caliber machine guns, 2 in each wing. The radiator installation becomes the most innovative feature. Schmued positions it in a ventral scoop under the fuselage, exactly at the aircraft's center of gravity. The cooling air enters through a small intake. It's beautiful, Atwood says, studying the installation drawing, if it works. In June, when they begin building the prototype, problems emerge immediately. The shop foreman, a veteran of 2 decades in aviation, says it's impossible. They're accustomed to building aircraft where a 16th-inch variation is acceptable. They develop new techniques, custom-made flush rivets, special sanding blocks, meticulous measurement procedures. The fuselage construction proceeds more conventionally, but Schmued's weight-saving obsession shows in every detail. The stringers, the longitudinal reinforcements, are spaced exactly as far apart as structural analysis permits. Bulkheads are lightened with stress relief holes. Every bracket, every fitting, every structural element is engineered to be strong enough, but not an ounce heavier than necessary. It's a racing aircraft masquerading as a fighter. He doesn't mean it as a compliment. Military aircraft are supposed to be robust, over-engineered, capable of absorbing damage and rough handling. The NA-73 looks almost fragile by comparison. By July, the prototype is recognizable as an aircraft. The wings mate to the fuselage. The tail surfaces attach. The radiator duct is fitted, its internal geometry matching Schmued's calculations exactly. The long, graceful wings place the landing gear attachment points far outboard, creating ground stability problems. "We're 300 pounds overweight," Waite reports in late July. Schmued studies the weight breakdown, identifies non-critical items, orders modifications, lighter radio equipment, thinner armor plate behind the pilot's seat, smaller ammunition boxes. 2 weeks of frantic weight reduction gets them to 7,100 pounds, still over target, but close enough. The prototype sits in the assembly hangar, nearly complete. Workers swarm over it, installing instruments, connecting control cables, rigging the flight surfaces. The paint shop applies a coat of silver aluminum paint and the RAF roundels that identify it as British property. The purchasing commission is paying for this aircraft. After all, it's 12 cylinders producing their rated 1,150 horsepower. Mechanics check for leaks, vibrations, anomalies. Everything appears normal. On August 10th, exactly 120 days after Kindleberger approved the project, test pilot Vance Breeze walks around the NA-73X prototype with Chief Engineer Schmued. The aircraft is beautiful in a purposeful way. Clean lines, smooth surfaces, no unnecessary protrusions or excrescences. It looks fast sitting still. "What do you think?" Schmued asks. Breeze, a veteran test pilot who's flown dozens of aircraft types, runs his hand along the wing's leading edge. "It's different, lighter than I expected. This wing, I've never seen anything like it. Is it really going to stay laminar? The wind tunnel data says yes. And this radiator scoop generating thrust? The mathematics say yes." "You're betting a lot on mathematics, Edgar." Schmued smiles thinly. "Mathematics doesn't lie. Intuition lies. Experience lies. Conventional wisdom lies. Mathematics tells the truth. Then let's see if mathematical truth can fly. But the first flight won't happen today. As Breeze begins his pre-flight inspection, a mechanical issue grounds the aircraft. A problem with the propeller governor. It takes 3 days to fix. 3 days past the deadline, but still an extraordinary achievement. They've designed and built a completely new aircraft in 123 days. On October 26, 1940, Vance Breeze climbs into the cockpit, starts the engine, and taxis the NA-73X to the runway at Mines Field in Los Angeles. The control tower clears him for takeoff. Breeze advances the throttle, and the prototype accelerates down the runway. At 75 miles per hour, the tail comes up. At 105 miles per hour, Breeze pulls back gently on the stick and the aircraft lifts off. The NA-73X climbs into the California morning, Schmued's radical ideas made real in aluminum and steel. The test flight lasts only 20 minutes conservative, checking basic handling, staying close to the field. But when Breeze lands and climbs out, his face tells the story before he speaks. "It's fast," he says simply. "Faster than anything I've flown. And the handling is ... different. Lighter controls. More responsive. That wing really works, Edgar. It really works." Schmued nods, allowing himself a moment of satisfaction. Then the engineer in him takes over. "What problems did you notice?" "Visibility isn't great. That long nose blocks forward view on the ground. And the radiator scoop, I can't tell if it's actually producing thrust, but it's definitely not creating much drag. You might have really pulled off the Meredith effect." Over the next weeks, test flights reveal an aircraft with exceptional performance for a fighter with an Allison engine. Top speed reaches 382 miles per hour at 13,000 feet. Range is extraordinary, over 750 miles on internal fuel. Handling is excellent. The laminar flow wing works exactly as predicted. But above 15,000 feet, performance degrades rapidly. The Allison engine, which lacks an effective high-altitude supercharger, loses power as the air thins. By 20,000 feet, the NA-73 is sluggish. At 25,000 feet, where combat increasingly occurs over Europe, it's simply inadequate. The RAF tests confirm it. Excellent aircraft ruined by wrong engine. They order 320 aircraft anyway, designating them Mustang MKI, but relegate them to low-altitude ground attack and reconnaissance roles. The U.S. Army Air Forces shows minimal interest. Edgar Schmued has created an aerodynamic masterpiece, the most efficient fighter airframe in the world. And it's being wasted on the wrong mission with the wrong engine. The transformation that will make the P-51 legendary is still 2 years away. April 30th, 1942. RAF Duxford, England. Excellent speed for this altitude, faster than a Spitfire MKV at the same height. But Harker isn't here to test low-altitude performance. He continues climbing. The handling is actually superior to most British fighters. Lighter aileron forces, crisper response, less adverse yaw and turns. At 15,000 feet, he notices the first signs of trouble. The Allison V1710 engine's performance begins deteriorating. The single-stage, single-speed supercharger adequate at low altitude simply can't compress enough air to maintain sea-level power as the atmosphere thins. At 18,000 feet, the Mustang is sluggish. At 20,000 feet, it's barely climbing. The engine is gasping for air. The laminar flow wing performs exactly as advertised. High speed with low drag, yet retaining good handling at lower speeds. The control harmony is superb, all three axes balanced. No tendency for one control to overpower the others. After landing, Harker walks directly to the telephone in the operations building and calls Rolls-Royce headquarters in Derby. "I've just flown the most extraordinary aircraft," he tells the chief engineer. "American design, North American Mustang. Currently fitted with an Allison engine that's strangling at above 15,000 feet. But the airframe, it's the finest I've ever flown. If we could fit our Merlin engine into this aircraft with its two-stage supercharger, we'd have something absolutely devastating. The suggestion isn't entirely original. The challenge is substantial. The Merlin is slightly larger, several hundred pounds heavier, and critically, its two-stage, two-speed supercharger requires different air intake and cooling arrangements. But the potential payoff is enormous. Combined with the Mustang's low-drag airframe and exceptional fuel efficiency. June 1942, North American Aviation, Inglewood. Around him, his engineering team debates cooling requirements, propeller clearances, center of gravity issues. The Merlin weighs 1,645 pounds compared to the Allison S 1,335 pounds, 310 pounds difference. We move the engine forward 7.9 inches, Schmued announces, pointing to the revised drawings. But it requires redesigning the engine mounts, the cowling, and the entire forward fuselage structure. The Merlin runs hotter than the Allison, particularly with the supercharger. Our radiator might not be adequate. We enlarge the radiator intake slightly and modify the internal ducting. The supercharger itself presents challenges. This requires additional cooling capacity beyond the engine coolant system. Schmued designs an auxiliary radiator for the intercooler, positioning it carefully to maintain aerodynamic efficiency. The propeller is another issue. Four blades provide better thrust but require different reduction gearing and a modified propeller hub. Schmued specifies a Hamilton standard four-blade constant-speed propeller, 11 feet in diameter. By August 1942, North American has completed the design modifications. The Army Air Forces, initially skeptical about the Mustang, is now interested enough to order 2 prototypes with Merlin engines designated XP-51B. But American Merlins will come from Packard Motor Company. The engine designation, V1650, producing 1,520 horsepower with 61 inches of manifold pressure. The first XP-51B prototype flies on November 30th, 1942. Test pilot Bob Chilton climbs away from Mines Field and immediately notices the difference. The Merlin's extra power is evident from the first moment: stronger acceleration, faster climb. But the real revelation comes above 15,000 feet. Where the Allison-powered Mustang wilted, the Merlin-powered version thrives. At 20,000 feet, Chilton is still accelerating. At 25,000 feet, the altitude where the Allison Mustang could barely maintain level flight, the Merlin Mustang is hitting 440 miles per hour. The aircraft is still responsive, still fast, still dangerous. It's a completely different aircraft, Chilton reports after landing. Subsequent testing confirms the performance leap. Rate of climb, 3,600 feet per minute. And most importantly, range, with internal fuel plus 2 108-gallon drop tanks, from England to Berlin and back with fuel to spare. From England to anywhere in occupied Europe and back. The escort range that has been impossible, that has condemned American bomber crews to fight their way into Germany without fighter protection, is suddenly, remarkably, achievable. But there's a war to fight, and the P-51B exists only as prototypes. The aircraft that could change the air war over Europe sits in a factory in California while, October 14, 1943, 27,000 feet above Schweinfurt, Germany. Bf-109s and FW-190s swarm through the bomber formation like sharks, attacking from every angle. The 50 caliber defensive fire from the fortresses is intense, but the German fighters press home their attacks with suicidal determination. The P-47 Thunderbolts that escorted the bombers from England turned back an hour ago at the limit of their range. Since then, the 291 B-17s of this raid have been on their own, fighting through wave after wave of Luftwaffe fighters. Ball turret to pilot 2 more going down, 4 o'clock low. Each fortress carries 10 men. By the time the surviving bombers stagger back to England, 60 B-17s have been shot down. 600 men killed or captured. 291 bombers sent out. Only 231 return. A 21% loss rate in a single mission. The strategic bombing campaign is unsustainable at these loss rates. Bomber Command calculates that at current attrition, the Luftwaffe is winning the air war simply by making daylight bombing too expensive to continue. The problem is simple. American fighters can't escort bombers deep into Germany. The P-47 Thunderbolt, excellent though it is, has a combat radius of only 375 miles, enough to reach the German border. The British have been saying for 2 years that daylight precision bombing is impossible, that the Americans should switch to nighttime, area bombing like the RAF. The catastrophic loss rates at Schweinfurt and Regensburg seem to prove them right. But in California, production P-51 Mustangs are rolling off the assembly line at North American Aviation's plant. 25 per week in November 1943, 50 per week by December. The Army Air Forces is finally taking the Mustangs seriously. The first P-51Bs reached England in November 1943, assigned to the 354th Fighter Group. The pilots, most of them experienced in P-47s or P-38s, are skeptical. They've heard the Mustang is pretty, but doubt it can survive combat. Fighters are supposed to be rugged, heavily armed, able to absorb damage. The P-51 looks almost delicate by comparison. Then they fly it. It's fast, reports Captain Don Blakesley after his first flight. Really fast. And it handles like a dream-like controls, responsive, no bad habits, but the range. The range is unbelievable. We flew a navigation exercise yesterday. 3 hours in the air, 2.5 hours at high power settings, and we landed with 30 minutes of fuel remaining. You can't do that in a P-47. The transformation Edgar Schmued envisioned, his impossible ideas about aerodynamic efficiency and range, has finally been realized. The mediocre low-altitude fighter of 1942 has become the premier high-altitude escort fighter of 1943. Now it just needs to prove itself in combat over Germany. That opportunity is coming soon.